Thanks very much. I'm both honored and a bit terrified to be presenting the entire field of quantum sensing in 10 plus 5 minutes. So I figured I would focus on what I know best and also what I think is probably most interesting to this audience, which is how to use quantum sensors to look for dark matter, which I think is a very exciting field that's definitely going to carry us forward into the next Snowmass process. So first, I should define what a quantum sensor is, but that's a problem because there's no universally agreed upon definition. One reason might be that one might be afraid that if you define X as a quantum sensor, then not X won't get funded. So there's been a bit of a resistance to actually, putting down some concrete definition. But let me attempt to give a classification with the caveat that these boundaries are fluid and different people might define things differently. So you can imagine a detector that can detect a single quantum of something using some kind of classical measurement. So here are two examples that come from dark matter experiments. You can detect a single quantum of light at the EV scale or a single quantum of charge by measuring some voltage. So then there are also the sensors that use some properties of quantum mechanics to sense very small classical things. And so the canonical example is a squid, which I'll talk a little bit more about in detail. So you use the fact that flux has to be quantized around this Josephson junction to be able to do very sensitive magnetic field measurements. There's also been a lot of recent work in optomechanics in using quantum properties of light to detect very, very small classical impulses, so forces. And then there are detectors that do both at once. So if you're using some quantum state, you can use that to detect the weakest possible classical signal, which is a quantum of something, because everything is quantized eventually. So you can then detect a single photon in a really interesting non-destructive readout technique that I'll tell you a little bit more about later. So this is basically the way the talk is going to go. I'm just going to show a bunch of pictures as examples and then kind of tell you what's interesting about all of them. And hopefully by that, I'll give you a survey of what's been going on in the field and where things are going. I should also say that, yeah, I mean, the progression of this session has, I think, been from formal theory towards the experimental side. And so like Hank, it feels a bit of a jarring transition because really, I mean, I'm showing you pictures of devices and stuff and I'm a theorist. So why should theorists care? And the answer is this picture. Raman brought up yesterday really nicely in his talk that one of the great mysteries right now in theoretical physics is what is dark matter? And as we've opened our minds to the possibilities beyond the WIMP, we see there's at least 50 orders of magnitude. If you extend it to the right, if dark matter is some primordial black hole, but really we should be figuring out ways to look everywhere. And the answer to why theorists should care about quantum sensors is that new ideas in the last 5 or 6 years have basically put flags effectively everywhere in this parameter space. I'm only giving a couple examples, a little bit self-serving because one of them is mine. But the fact that there are ideas that are letting us cover these 50 orders of magnitude in dark matter parameter space is very exciting. And this is only going to continue. And so I really think this is an area that we should continue to push on. And one interesting example, maybe the dark matter analogy to kind of the exascale quantum computer is some kind of detector that can detect dark matter that's only gravitationally coupled. And let's face it, that nightmare scenario has always been a possibility. If dark matter doesn't have any interactions beyond gravity, well, we know it's out there. We better be able to see it on Earth. So we should be able to use some detector to see it gravitationally. There's some ideas to try to do that if dark matter is very heavy, and maybe if we get lucky, we can sort of even push it farther down. Okay, so let me talk about these single quantum detectors. So of course, these have been around for a century, right? The first bubble chamber experiments for detecting single particles. And we do this at the LHC all the time. Every particle seen at the LHC is a quantum. So what's new here are lower energy thresholds and low dark rates. In other words, the spurious rate at which your detector fires, even if there isn't something to see. So one example of the low threshold detectors are these single charge semiconductor detectors, taking advantage of the amazing work that's been done in fabrication of silicon for the computing industry over the last 50 years. So Sensei is an experiment that uses this thing called a skipper CCD. So CCD is the thing that's in your phone that detects photons. But because charge makes light and light makes charge, you can also use it to detect something that scatters in your detector and makes a single electron hole pair. You drift it very slowly, and then once it's at the surface of your silicon wafer, you can kind of move a charge back and forth in order to measure it multiple times non-destructively. That brings down your noise and lets you really measure, is there a 1, 2, 3 electrons per pixel. Then there's also the idea that's been exploited by the CDMS collaboration in their original incarnation as a WIMP experiment, but that was understood now that can do these low threshold single charge measurements. If you make an electron hole pair and you rivet through a semiconductor with a large voltage, it will shed phonons or make heat. And the amount of heat you get is proportional to the number of charges. And so you can count again, if you make 1, 2, 3 charges. And so the threshold here is just set by the band gap of silicon, which is about an EV. So you need an EV of energy to make an electron hole pair in the first place. But once you do, you can measure it either kind of drifting it slowly or drifting it very fast. So there are also these amazing superconducting nanowire photon detectors that, developed by several groups, including at NIST and at MIT, that have been used in 2 different ways for dark matter experiments. So the idea is if you have a very small deposit of heat from, say, an infrared photon, then a superconductor is going to undergo a massive change in resistance, and that's a macroscopic signal that you can measure. And so recently these are used both to set limits on dark matter, because that can act kind of like photons. So that's this lamppost experiment that Masha's going to talk a lot more about tomorrow. And then also on just dark matter electron scattering, where that energy deposit can also give you that localized phase transition, and then you'll be able to see it. But the thing that I want to focus on here, this is the dark rate of the detector integrated over 180 hours. There's 1, 2, 3, 4 events. So that's just crazy. And I mean, the thresholds here are also about an EV. But there's hope to be able to push this to lower thresholds. But a detector that really only clicks 4 times in 10 days is the kind of thing that you can imagine eventually becoming a real background-free experiment. Okay, so where are you going in the future? So a single quantum of something that we haven't been able to see yet is a single phonon, so a quantized lattice vibration. That spectrum extends down to 0 energy because there's always acoustic phonon modes. But there are these optical phonon modes that have energies around 50 millieV, and eventually we'd like to be able to see those if dark matter is undergoing nuclear scattering. It doesn't talk to electrons, or even if that's the if that's a dominant signal in your detector. You're using these transition edge sensors to do that too. And then a collaboration that I'm part of, the Splendor collaboration, is using exotic narrow gap semiconductors to lower the threshold for charge detection. And there's a really strong synergy with condensed matter because you need kind of exotic materials that have these very low band gaps in order to do that. Okay, measuring classical things quantumly. So the 2 examples that I'm going to focus on are squids. So the flux quantization around a Josephson junction, you can bias the current around it to sit at the right point on the flux versus voltage curve, such that a tiny change in flux is going to give you a large change in voltage. That'll let you sense weak magnetic fields. This is what's used by the abracadabra experiment. And then as Hank mentioned, there are these high quality factor SRF cavities where a gigahertz photon lives for 100 seconds. So that you're using some property of superconducting niobium alloyed with some other stuff to really increase this Q factor that lets you detect very, very weak E&M fields that can ring up over a long time. Then there's this complementary idea of using optomechanical systems for force sensing, where you interrogate something or you suspend something with some laser, and then you're able to see very, very small impulses on that thing by shining light off some mirrors. And this can, of course, be extended to even heavier and heavier objects. This is, in some sense, what LIGO does. You're using macroscopic objects that are suspended, and then you're doing kind of quantum readout of those objects. And so here you can imagine, dark matter coming in. If there's some dark matter nugget that exerts some large force on this microsphere, then you might be able to see that. Okay, so to do better, so some of my colleagues sort of call this quantum 2.0. You actually need to measure or prepare an actual quantum state. So an example from how this works with axion detection. So the standard way of looking for an axion in a cavity is to read out the power in the cavity. There you're kind of reading out amplitude and phase at the same time, so you're hit by the standard quantum limit. You just look for an excess of power over your noise. This is what ADMX does. So 2 ways that you can do better are if you couple your cavity to a qubit, you can exploit the fact that the occupancy of a photon in the cavity shifts the resonance frequency of your qubit. So you can do non-destructive readout by interrogating the qubit frequency to understand how many photons are in your cavity. And this is beautiful work done at U Chicago and Fermilab. Or you can prepare a vacuum state that's not the thermal vacuum, that's a squeeze vacuum where you put kind of the noise where you don't care about it, such that your signal is going to displace you in the direction where the noise is smallest. This is this work that was done at NIST and Yale to improve the scanning rate of a haloscope for axions. Okay, good. So I have 1 minute left. So why are theorists crucial? So here I've departed a little bit from the bibliographic convention of just listing the first author, only to show you that every single one of these pictures has a theorist name by it. So what can theorists do here? The answer is a lot. So first, we can define theory targets. Where should these experiments look? This is this, wonderful plot from the Cosmic Visions report that I cite basically every time I talk to people about this field. Where should we look for dark matter electron scattering? Well, there's some models, there's some limits. We know that our targets want to sit here, and if once we've done that, then we move on to the next one. You can do the same thing for axions. Inventing new uses for existing sensors. NIST has been developing things like this for decades. Anything that can measure things ultra precisely, we can figure out a way to use. All it takes is some creativity. So this is, for example, this idea from Dan Carney, Gordon Kernayich, and others to do an array of these levitated spheres to look for the gravitational displacement of stuff by passing dark matter. So theorists can also spur development of new sensors. They can suggest ways to modify existing sensors to better suit our applications. So the Sensei collaboration, kind of going from these CCDs that have already existed to skipper CCDs, where you improve your noise by doing these multiple measurements. That in part was spurred by the need to have that very, very low noise for dark matter. There's also interesting ideas from my colleagues at UIUC for looking for very, very low energy phonons in superfluid helium. And then also, kind of the phenomenology that theorists traditionally do can really be applied to this low energy data too. We need to help interpret the data. And there we really need to exploit our connections with our condensed matter colleagues, because all of this stuff, all these events are happening in stuff. And condensed matter detectors are wonderful and interesting and beautiful and complicated. And so theorists can play the role of kind of understanding these anomalies in these detectors and trying to come up with theoretical models that explain them. There's a lot of work to be done in all these areas. So just to wrap up, you don't have a real experiment until you have a clever acronym, a website, and a picture of a theorist standing by a machine with a wrench. So just to prove to you, these are ideas that went from theory paper to first data in less than 5 years. So this is the dark SRF experiment, based on an idea proposed at Stanford. Actually, I think maybe a little bit longer than 5 years for this one. Now a running experiment at Fermilab. The Sensei collaboration, which you probably all know, that won the New Horizons Prize last year. The Abracadabra experiment that I'm part of, and then the Wind Chime project, which is this gravitational detection. So this is a rapidly advancing field. Much more progress remains to be made. I think that, this feels to me a lot like I imagine the way that physics was done 100 years ago, where the close collaboration between theorists and experimentalists let you basically iterate ideas on an extremely rapid timescale. I find it very exciting, and I think it's something that we should all continue to support. Thanks.
So thank you, Yoni, for that very nice talk. So we have time briefly for a couple of questions at the back there.
Hi, thanks for a very nice talk. So one of the most well-developed kind of quantum sensor is like atomic clock, nuclear clock, or molecular clock. Of course, nuclear clock is being developed.
Yeah.
So what do they fit in your picture? And also I want to ask the space version of them. Where do they fit in your picture or description?
Sure. So I should have said as a caveat, there's an enormous field of quantum sensing, and just because I didn't put something on my slides doesn't mean it doesn't exist. Obviously, atom interferometers have been around for a long time. So one thing they can do is they can look for lower frequency gravitational waves. You could also look for oscillation of fundamental constants that might come from very, very low mass dark matter. All these things are possible. If you go to space, obviously the noise is less in a lot of respects. So yeah, that's another example of a quantum sensor that I just didn't have room to show on my slides.
Thanks for the great talk. I have a question, I think, about part 3. So
Yeah.
How close to the so-called quantum Kramer-Rao bound does one get? As I understand it, it means error bar of order 1 over n experiment rather than 1 over square root of n from the effects of the entanglement.
So I do not know quantitatively. I know that the figure of merit that I know, for example, from the squeeze vacuum is that they're basically able to improve on the standard quantum limit by about a factor of 3. Again, I'm not sure where you put that factor of 3. I think that basically means just the ratio of the major and minor axes of this error ellipse. But maybe somebody who knows more about the formal aspects of this might be able to give you a better answer.
Okay, thanks.
Anybody out in Zoom land? Okay. I guess you folks talk to the LIGO people somewhat. The technology must be very similar.
Yeah. I mean, and the ideas from LIGO have really, one can imagine them finding use immediately in dark matter searches. I know that like Yue Zhao at Utah has been. Well, I think he's on LIGO, and he's also using basically just LIGO analyses to look for light dark matter that will do similar things to the interferometer arms that the gravitational waves would do. I mean, I think the idea of sort of using quantum mechanics to interact with macroscopic systems is going to be imperative for dark matter detection, because just to get enough event rate, you just need a big block of stuff. So it's going to be very hard to see, I think maybe one of the issues of looking for dark matter with kind of these atom interferometer setups is you just don't have necessarily Avogadro's number of atoms you can put in some nice quantum states. If you can manipulate some macroscopic system, then you'll have a better sensitivity.
Okay, let's thank Yoni again. Thank you.